tools. We just need enough people to ask the right questions. And it's a fascinating time, and I think on all of these to be involved.
I don't remember the name of the person who said that, but like science is being at the forefront of ignorance.
Oh, yeah.
And I should find that quote, like the person who said that. But we are really there. We don't know what's happening. But we are starting to have the technology and the tools in all the molecular mechanisms to make molecular tools to get into the mechanism inside the cell, and then try to figure out where the cells store that memory. It's probably not going to be stored the same way it is stored in neurons, but maybe it is actually.
And that's the thing is like what I find fascinating is that these systems at the base of the
And now for something completely different.
I started a show full of fun and unintentional things. DaHoShow, streaming on YouTube for thee. DaHoShow, the courts have compelled me to warn you, it's me you will see. Streaming and gaming and talking and fussing. DaHoShow, it's free. Oh, say, I started a show full of fun and unintentional things. DaHoShow, streaming on YouTube for thee. DaHoShow, the courts have compelled me to warn you, it's me you will see. Streaming and gaming and talking and fussing. DaHoShow, it's free.
So we're going to be talking about not just creatures that you wouldn't expect, but the idea of bringing things together and bring in the next two people. One of them is a MacArthur Genius Award winner and professor of engineering at Princeton, where she studies collective intelligence in bird flocks, fish schools, ants, honeybees, zebra herds, and robots. So please welcome Naomi Leonard. And our final guest is a biologist, author, and photographer, research associate in the Department of Entomology at the Smithsonian Institution, and a visiting scholar at the Department of Human Evolutionary Biology at Harvard. Please welcome Mark Moffat. So, speaking of swarm intelligence, there are leafcutter ants. And I just actually was reading today that ants have the largest brain per body mass of anything. Is that true?
Of anything?
Of ants.
Well, I would guess humans have larger. But as Darwin said, the brain of an ant is the most marvelous atom in the universe because of what it can do. So,
can you talk a little bit about this amazing society of leafcutter ants and how they function together?
well, the message I always give to folks is that ants are really marvelous because some of them, particularly ones with large societies like the leafcutters, are really much more like humans than chimpanzees. Ants have to figure out all kinds of problems that no chimpanzee has to deal with. And the leafcutter ants is an example. There are lots of differences. They are aliens compared to us, but the similarities are marvelous. And leafcutter ants, for example, we have the video of them carrying leaves, build highways that are very marvelous things. They build about 3 kilometers of highway a year in some colonies. These are colonies, these are pictures of mine from the air in Paraguay showing nests, which are as big as this room and as deep as this room. So these nests are enormous, and that white sand is just something they've brought up from deep below ground. And those are highways going out in all directions. And they're carrying back those leaves you just saw in that previous video. So in the next picture, we can see what happens. This is below ground, as they say, very complicated architecture, all kinds of work going on there by the ants as we're excavating into this working skin. And they have an air conditioning system that keeps everything cool and oxygen involved. Next slide demonstrates what they're doing, and you may not guess why. But they have these leaves. Their claws are about 40% distinct, so they're limited can openers. Have the leaves like this, they actually vibrate their bodies like electric current. And this is a certain kind of ant that's good at this task, and it carries it back to the nest. Shown in the next slide, that they do not eat leaves. It was thought for a while that they might, but what they do this is a fungus that was domesticated many years ago, and the ants have all the elements you might think of farming here. First of all, they have special calls. They have to produce the leaves, they grab them from mulch, and then insert by hyphae, big plants. They have to deal with various pests, so they have pesticides, fungicides that get rid of anything that doesn't suit them. And every size of ant, and there are different sizes that do different duties, has a different one of these tasks. The leaf-cutting ants are relatively large, and you go down and down in size to the smallest ants are actually involved with keeping those gardens pure, plucking out anything that doesn't belong there. And the next slide shows that smallest ant doing that task. And this is a domesticated fungus. They domesticated this fungus about 40 million years ago, became fully dependent on the ants. And like domestication in humans, it means that we're doing all the work. The fungus are getting a free ride like the wheat plants are. The wheat plants have conquered the universe because of us. There's so many more wheat plants than anything else. And these fungi actually have little nodes on the tips that have the complete and balanced diet of the ant in them. Those little white globs there that you see in the face of that ant gives them anything they need. Next. So this is just going through the story. Now the communication of these ants, they're not brainless, but it's pretty small. And it involves simple signals. I'm particularly interested in identity, how these societies stay apart.
Some of these ants have more muscles in their head than they have brains.
They do, yes. And, I would think that, I feel like I'm comfortable with that. But the smallest ones probably don't, but the soldiers definitely do. The soldiers are big and dumb. And they just know how to cut you up as if you were a leaf. And most of these cues are signals are going back and forth between them as they touch each other. And ants can actually determine many things when they're walking down the trails and you see them stop for a second in front of each other. They actually can determine, and shown for some species, what the other ant is doing, and they will assess as they go on what the ants in the colony are doing by the ones walking by and decide themselves what they're going to do that day. And so this leads to a very efficient society. And right down to the last detail on the last slide here, I said that ants are doing all kinds of things that chimpanzees don't do. And I can tell you one thing chimpanzees don't do is worry about public hygiene and health issues. And this is an ant that's a trash collector, and you can become a full-time trash collector in an ant colony. And believe it or not, you can become a specialist at old trash or new trash, moving dead bodies to the grave site. That's a job. And burying this stuff about 30 feet down in some of these large colonies, which is equivalent to us putting our worst hazardous waste 3 kilometers below ground.
Don't give bad ideas.
Oh, yeah. And they build these chambers just for the waste that are as big as a coffin for a small child. Not a nice image, but it's pleasant inside. And you can imagine how many millions of years combined of all these thousands and thousands of ants it takes to make a chamber that big, that far underground, just for public health reasons. And the reason for that is the diseases that might carry could destroy the gardens. And these ants live and die down there, producing this into a mulch that becomes harmless. So that's some of the story of how these particular ants work, which are among, of course, the more complicated species out there, which is why I picked it up.
So, who's making the decision? I mean, who's the boss?
Now, and the super intelligent ants would wonder what the heck humans are doing. Apparently, we keep some guy in the White House, and if we just take them out, we can, like, take over the whole country. What is that about? I mean, have you ever tried to stop ants? You can step on them all day in your kitchen, and they're just going to keep coming. And having no leader is a way of being very functional as long as you're organized enough and everyone has enough information to make the right choices appear in aggregate out of all these individuals.
So, do you think of each individual ant as like a neuron?
Well, it's an interesting thing because basically a large ant colony, an ant colony like the leafcutter ants or a large army ant swarm, has an aggregate, the same number of neurons that we have in our head, but distributed among many individuals. So you can ask yourself, what leads to the best result? Putting all our eggs in one basket so that a single bullet in our head can destroy us, or distributing ourselves. I think of it as a kind of Marvel comic superhero. Imagine if you could fall apart into a million pieces. You're starving to death, but you fall apart into a million pieces, and these little mini brains go out and find food that you could never find underneath things, feed you, and they come back together, and there you are again. You start, composing music or whatever you can do with your brain in one place. Only ants and humans have societies of millions and sometimes billions of individuals. And once you have a lot of individuals who have to deal with public health issues in a way that no other vertebrate other than humans does, it has nothing to do with intelligence. It has to do with the fact you have to put together a society that stays healthy, brainless or not.
Naomi, you've been studying sort of collective behavior of other animals with small to middling-sized brains, like ant swarms, honeybees, schooling fish, bird flocks.
Right.
What we're learning from those kinds of swarming behaviors?
Well, starlings are actually stunning, not just beautiful, but remarkable in what they can do. I mean, they inspire me every day. I mean, I started working on these problems in the context of design of sensor networks of robotic vehicles. On program up their computers so they would communicate and sense one another.
Salt the earth, boil their seas, drive them before you!
There's so much uncertainty, so many things can happen, it's so opaque. And to solve these kinds of problems, I had to make a swarm that would be sensitive to information in the environment that was important, and then also insensitive to all these uncertainties and perturbations and noise. And when you look at these kinds of bird flocks, fish schools, or ant colonies that forage in harsh environments, and I started working with biologists, I learned that these animals actually balance this kind of trade-off between being able to be super flexible, being able to be super responsive to and sensitive to signals that matter. A predator, food, a migratory route that they have to figure out, and then not be concerned with some kind of disturbance or false positive. And so the questions that I've been looking at really reach into those contexts and actually use the connections between individuals as neurons and the group as the swarm as a brain, because there's a lot in common in these settings in the design setting, I'm asking these questions. How do I give these individuals rules to respond to what they measure about the environment, to respond to what they sense about the neighbors that they can see or hear or communicate with, so that at the level of the group, they're flexible and responsive, but also robust. And in the animal world, the biologists that I work with ask the same kinds of questions with the opposite direction. So they observe these behaviors, and they want to know what it is that individuals are doing. So what are the underlying responsive behaviors?
There is much to be done.
For individual fish or an individual bird, how does it respond to what it senses about its neighbors? And it's not just that they're moving in different ways. They're actually moving to carrying out tasks as they move. So what might look like this aerial ballet, we saw that earlier, is probably more likely an evasion of a predator or a foraging activity or sensing and learning about a migration. And it's just remarkable that they can do this. And so in my work, my work is involved in trying to understand mathematical and physical principled perspectives. What are those interconnections? What is it? What are the rules that animals are using? What is it about my neighbor that elicits a response? Simone starts running this way. Am I going to follow him? And what if Mark runs the other way? Do I split in half?
Yeah.
So good evening, I'm Robert Krowich. I'm Brian Green, and I'm going to give a bit of an overture to some of the ideas in this Infinite Worlds program that we're going to be hearing about tonight. And one way of framing the discussion, the conversation, is to recognize that over the past few centuries, our understanding of the universe has really increased by leaps and bounds. I mean, the festival programs over the last few days cover a tiny fraction of the tremendous insights that we've been fortunate to achieve. But there is one unexpected, perhaps, implication of the insights that we've found, which is that we have gone through a kind of demotion, a variety of discoveries that we had. I mean, you think about it, a long time ago, right, we thought the Earth was the center of the universe. Then people like Copernicus and Galileo come along. We recognize, no, the Earth goes around the sun, but we thought the sun was the center of the universe. But then, no, we realized the sun is one star out of perhaps hundreds of billions in our galaxy. And then Hubble and others come along and we realize that even our galaxy is just one of many, many galaxies. What we're talking about here tonight is perhaps one more step in that kind of demotion from being at the center. It's the idea that perhaps our universe is not the only universe. Perhaps there are many universes, here is one of them. The image to have in mind, perhaps, is that the universe is a big cosmic bubble bath with all these different bubbles, these different universes. Our universe is one bubble in the entire whole. So what I'd like to do in a few minutes of preamble here is give you a sense of the essential ideas that lead up to this kind of notion, and then we'll follow it on with a panel discussion where we explore things in more detail. Now, the key physics behind all of this is the physics of gravity. So let's start there. So gravity, we all know, Newton gave us a way of thinking about gravity way back in the 1600s. He basically wrote down an interesting formula, an equation that tells us that any object in the universe attracts any other with a force, the force of gravity, that depends on
just two things: how big the objects are, how massive they are, and how far apart they are in space. Very simple equation we teach to high school students still today, hundreds of years later, and we make use of that same equation when we're trying to get a rocket ship to land on the moon or to rendezvous with some other astrophysical body. So it's a very powerful way of thinking about gravity. Nevertheless, Albert Einstein realized in the early part of the 20th century that there was something deeply missing in Newton's physics of gravity. And it was simply this. Newton wrote down a formula that describes the force of attraction between two objects, but he never explained how it is that those objects exert that attractive force, how they exert a gravitational attraction between them. And Einstein deeply wanted to figure out the mechanism by which gravity operates. And in a famous story, he started on this journey to figure out the mechanism behind the force of gravity by going to Newton's Principia, the book that has all the results in math and physics that Newton studied his lifetime. Read it for tonight's discussion. You're all familiar with this. In fact, I was a little bit surprised that the brochure said you had to read it in the original Latin. I've never done that, but you guys are a step ahead of me. So, Einstein goes over to the book, looks under G, finds the law of gravity, goes a little further for subheading M, the mechanism by which gravity operates, and there he finds something surprising, because Newton basically says, I don't know how gravity works. I can write down an equation describing its strength, but how it exerts that, I don't know. In fact, in his own words, he said, to the answer of that important question, the mechanism by which gravity operates, he said, I leave it to the consideration of the reader. Now, most readers would read that and read on. Einstein, he spent 10 long years trying to figure out how it happened. Finally, by 1950, he came to the general. And the answer is subtle, it's beautiful. There's a quick way of sort of thinking about what he found. It's simply this. Einstein said that if you have the sun here and the earth here, and the basic energy space of the force of gravity must somehow be mediated by space. Space itself must somehow be the mechanism by which gravity exerts. And the way of thinking about that, first, I'll show you a picture in just a moment, is forget about gravity for a second, use an analogy that physicists love in the setup. Imagine you have a rubber sheet stretched in front of you, nice and taut. Take the marble, you put it rolling on the surface, it goes in a straight line. Picture it. And now take a heavy object, I put it in the middle of the sheet, I set that marble rolling, it won't go in a straight line. Einstein says, take that simple idea and apply it to all around it. And he said, when object is in space, object is in space is curved. That way, you have to get an idea what that looks like.
It's too far away.
We envision the fabric of space as sort of this grid-like icon. This is now 3D space, so it's a little hard to view the visually. So rather, let's go to a two-dimensional analog to capture all the ideas. Here you see space is nice and flat, nothing is present, but when the sun appears, the fabric curves. Similarly, look at the vicinity of the Earth, the fabric curves a bit. Now, focus your attention. The moon is kept orbiting, rolling along the valley, curved environment. That is how gravity is communicated. That is the mechanism for exerting the gravitational force. If we pull back, the Earth, too, is kept in orbit because it is rolling along the curved portion of the spatial fabric that the sun creates.
I'm out of range.
That, Einstein said,
I need to get closer.
Gravity works. Now, he wrote down this theory, 1950.
It's too far away.
Quickly, people around the world began to think hard about this general view of physics ideas. And in particular, there was this interesting physicist, a Belgian priest who was also a physicist, who got hold of Einstein's work and decided to apply Einstein's ideas not to the sun, not to the earth, but to the entire universe. And when he applied Einstein's idea to the entire universe, he found something very interesting. He found that the fabric of space is made either contracted or not sitting still. So he envisioned that perhaps taking one of those solutions that the universe might be growing in time, might be expanding. Now, he brought this idea to Einstein, and Einstein said to him, "Your mathematics is fine, but your physics is abominable." And what he meant by this was he'd already been through this drill. There was an earlier physicist, Alexander Friedman, who I decided to say, just like my for tax rate. And Friedman has already found this idea of hold on, got it. Einstein at first thought that Friedman had made a mathematical mistake. Friedman was no mathematical error. So maybe the same idea. Einstein would say, yes, the math is right. We're saying your interpretation of the universe is expanding. That's just look out at the sky. Not.
We need to target
So Einstein was very, very clear in his own mind about how he thought the universe should behave. In fact, so certain was he that he went back to the mathematics of general relativity and tinkered with it in order to get rid of this possibility that the universe might be expanding. What happened next is quite wonderful. In 1929,
I need to get close.
Examined the motion of various objects, galaxies, in his telescope at Mount Wilson Observatory, and found indeed that the distant galaxies were all moving away in a very particular pattern that was consistent with the fabric of space itself stretching. It's as if you found the galaxies are kind of sewn in the fabric of space, and as the fabric stretches, the galaxies all pulled apart. The universe is expanding. And so what this gives rise to is what we conventionally call the Big Bang. This is about starting out small and growing in size. So just pictorially, what that would look like is, imagine that the universe begins really small, dense, hot nugget, it then expands, space expands. And as space expands, this hot primordial plasma in the beginning cools down. As things expand, they cool. And when it began to cool, structures would begin to coalesce. Structures that would ultimately give rise to the galaxies, the stars inside of the galaxies, and give rise to the kinds of things that you see on a nice, dark, clear night sky. So this was the picture that ultimately emerged from this way of thinking about gravity and the way that the universe evolves over time. Now, I don't want to give you the impression that everybody immediately believes this way of thinking about the universe. There is definitely a need to try to find yet other experiments, other observations that would convince people that this is the right way of thinking about the origin and evolution of the universe. And there was one particular individual, George Gamow, who played a very important role in this. George Gamow is a very interesting character. He was a 6'4" hulking Russian physicist who was as quick-witted and fun-loving as he was hard-working. And he and his wife tried to defect from the Soviet Union in a very interesting way. They took a kayak, filled it only with brandy and fine chocolate, and set out to cross the Black Sea. Now, 36 hours after they started on the journey, they were picked up by the authorities. They were around, and it was really lucky that the business were only brandy and chocolate, because that corroborated the story that they were just out sort of for an afternoon paddle. They weren't actually trying to defect. But anyway, so Gamow, a few years later, was successful in slipping past the Iron Curtain, comes to America, and begins to think about cosmology, Einstein's ideas, and realizes the following very simple idea. If the universe began very small and very hot and then expanded, when things expand, they cool off. That means a little residual today all around us left over from he said we should look out and try to find that residual protein. That will corroborate the picture that the universe began very small and very hot.
I don't have a
in the beginning. Now, it's a wonderful paper. put it out there, but he couldn't convince anyone to actually look for this radiation that goes to the Big Bang. Part of the reason was most scientists were focused on quantum mechanics and other aspects of physics, not in cosmology at that particular point. But the other reason why people didn't really jump on this, at least in part, was Gamow was kind of had a reputation as being kind of a jokester, kind of a trickster. I mean, it was once writing a paper with a student of his who played a vital role in this recognition that there should be heat left over from the Big Bang, a student named Ralph Alpher. And what Gamow did was he convinced this fella over here, not the one on the right, the one on the left, he convinced Hans Bethe to put his name on the paper for the sole reason that then the office would be Alpha Beta Gamow, which is kind of, passable for a physics joke because the standards are not particularly high. But it did leave people with this impression that he wasn't as much as he deserved. So the paper that he wrote with Alfred and also with Robert Hermann basically died. Nobody really followed up on it. A few years later, because great ideas in physics ultimately will be rediscovered if somebody doesn't follow it up at the initial time it was thought about. This fellow over here, Robert Dickie at Princeton and Jim Peebles over here, they came upon the same idea, that there should be heat left over from the Big Bang. They went through a similar kind of calculation. Now they were an interesting pair because Dickie was a great experimentalist, so they started to actually build the equipment to try to find this heat left over from the Big Bang. Middle of their work, they got a phone call from these guys, Arno Penzias and Robert Wilson, a phone call that perhaps is the most famous phone call in the history of cosmology. I guess it's not that impressive. It's sort of like being the skinniest kid at bat camp or something like that. But it really, I don't want to downplay it. This was an incredibly important moment because these two guys who were about 30 miles from Princeton working at Bell Labs, using that antenna that you see behind them, picked up a hiss. And it turned out that hiss, they tried to get rid of it with also, they tried to clean the equipment, they couldn't get rid of the hiss. Finally, they realized that this hiss must be heat, the radiation left over from the Big Bang. So they called up Dickie, told him that they found this, and Dickie basically put down the phone and said, "We can scoop. These guys found it. Indeed, they won the Nobel Prize for this particular discovery." So this kind of confirmation of the notion of the Big Bang was a very spectacular moment. And it also was a key watershed because this was when cosmology entered the realm of a quantitative science. Because their observations, as well as others that have been carried out since, there's been a second Nobel Prize, Mathers and Smoot, for these observations, gives rise to a way to test these ideas. Now, what I'd like to do in the next transparency is show you a graph, a theoretical curve. It doesn't really matter if you understand exactly what it means. It's telling us the amount of heat at every particular frequency, the number of photons at every frequency that should be all around us, left over from the Big Bang. And then I'll show you the actual data. So take a look here. The curve will start to, from the left, go up toward the right. This is theory. This is what the Big Bang theory says. And now let's see what the observations say. And there'll be little red dots. And notice that the little red dots are following right along the curve. A very impressive match between theory and experiment, allowing people to believe that this is the right way of thinking about the universe. Now, this is great, but there were still a number of unresolved issues. And we'll talk about some of the issues in just a moment when the panel begins, but one of the biggest was, when people look more closely at the Big Bang theory, they realize that the Big Bang really tells us how the universe evolved after it started expanding outwards, but it doesn't really tell us what drove the outward expansion. It kind of leaves out the bang. So the question was, what's the bang in the Big Bang? And it's hard to figure out what that would be. Normally, gravity pulls things inward, so what would be the outward push that would get the universe to start expanding in the first place? Now, there were a lot of ideas that were put forward on this. Some more convincing than others, but there were these two guys here, Alan Guth and Andre Linde, also Paul Steinhardt at Princeton and Andreas Albrecht, who actually came up with the answer that we believe today is probably what happened And you're going to meet these two fellows in just a moment. But the one thing I want you to take away from this slide, which is amplified by bringing Friedman back into this, modern cosmologists are really happy. So anyway, what did these guys find? What they found is the following. Going back to Einstein, this really comes from Einstein himself. Gravity, according to Einstein, is not only an attractive force. Newton thought it was only attractive, pulls things together. These guys realized, amplifying Einstein's insight, that if there's a kind of energy suffusing space, the word field may come up in the conversation later on. If there's this energy, this field that's suffusing space, it can give rise to a repulsive gravity, an outward pushing gravity that can cause the universe, in some sense, to fly apart, to be pushed apart, to give the bang in the Big Bang. So the picture that you come to in a framework called inflationary cosmology that we will discuss in just a moment is there's a little tiny nugget, that little bright area on the left-hand side, a little tiny nugget of space gets filled with this energy, gives rise to this incredible outward push, causing the universe to expand and carry on in the expansion as we witness today. That's inflationary cosmology. Now, the one thing that I want to call out here, because the key thing that I hope that you'll take home tonight is cosmology is not a bunch of theoretical ideas that people just posit and hope that they're right or wrong. It's become a quantitative science. So the most quantitative way of understanding, of convincing yourself that this is true, comes from an understanding of, again, heat left over from the Big Bang in the following sense. When the universe is very tiny, there is a feature of quantum physics. You don't need to know much about quantum physics, but quantum physics says that there's always a certain amount of uncertainty, a certain amount of fluctuating behavior happening. And that would happen at the far left when the universe is really tiny. But when the universe expands, the jitters of quantum mechanics get stretched out. And when they get stretched out, they give rise to hot spots and cold spots in the sky. Tiny temperature differences, not much. 1 part in 1,000, 1 part in 10,000 or so. But these tiny temperature differences, in principle, can be measured. And let me just focus in. If you see the green and yellow, those are indicating different temperatures. Actually did it in blue and red here, but it's the same thing. These are hot spots and cold spots generated by quantum fluctuations in the early universe. And the idea is that if you have a device, a satellite over there, it can measure those hot and cold spots. The light travels to the satellite. And let me just show you in a final little convincing piece of data what you find. Here is the theoretical curve coming from quantum physics and inflationary cosmology. Here is the data. And I will just sit back and let it go. Now, this is data that was set down 13.5 billion years ago. This curve is generated by us humans 13.5 billion years later. And the data and the curve match to fantastic precision. Were you to ask me what the most beautiful picture that our civilization has produced? Yeah, I mean, certain things do come to mind, you know, Starry Night, Mona Lisa. This would rank for me among those. That's how spectacular this picture is, this agreement between theory and experiment. Now, the final point that I want to make before I'll be done, which really ties it into our program, is this. The discoverers of this inflationary cosmology realized a couple of years after the initial discovery something quite interesting. This kind of inflationary burst is likely not to be a one-time event. There can be many of these inflationary bursts. In fact, the picture which I like to have in mind is like a big block of Swiss cheese. And what I mean by that is if the Swiss cheese, if the cheesy part of the cheese is this energy that's suffusing space, the idea is the cheese expands, but in various locations, the energy dissipates and creates a little opening, a little bubble that then it grows over time. And the idea is that all of the little bubbles in the cheese are different universes, our universe being one of those bubbles. That's the way in which many, many universes come out of this inflationary cosmology. Let me show you a visual of what that would look like. Final one here. So what we'll see coming into view here is a misty, gas-like entity, which will be like the cheese that I was describing. It's that energy, it's that field, suffusing space. So here it is coming into view. The universe is expanding. This is creating a repulsive gravity, pushing everything apart. But at various locations, pockets open up, regions where the energy has dissipated and turns into more ordinary particles, like matter, and radiation. So these would all be, in this picture, different universes created within this vast, expanding object. We call this the multiverse. Now, if we go into one of these, it looks, once you penetrate it, just like an ordinary universe, like our universe. So here is our universe, just one bubble in this cheese. So the fact that it's a bubble, it looks small from the outside, it's not. It's huge from the inside, something we can talk about in the panel. As you see, we've got galaxies all through here. This could be our universe. Now, if we exit, just to take a look at what it would appear to be in another bubble, let's meander around, focus in on one. If we go into another bubble, the world physics can be a little bit different. The features do not have to be identical to ours. So all of these different worlds, all of these different universes would be out there embedded in this vast, expanding, gaseous realm, with our universe simply being one of the bubbles among many. So the idea is, if this picture of the universe is correct, and we could take, say, the grandest view of the multiverse, we would see a vast assortment of worlds where various nuggets of reality would play themselves out world by world as they evolve and change, as they go forward and back, as they grow in size. The universe, in some sense, would be this vast assortment of little bubbles, with our universe being but one melodic line in this richly textured cosmic score.
Claire Chase on flute, Rebecca Heller on bassoon, Eric Lamb on flute, and Joshua Rubin on clarinet. So thank you. I'm Robert Krolwich, the aforementioned, and so I just want to just reset the stage here, because when Brian does stuff like that, he does it so well that you all go, oh yeah, you know, but I just want to be careful here. Because very, very recently, for most of you sitting here in front of us here, you thought, as did I, that universe meant all that there is, the whole shebang, you know, everything you can imagine. And because the universe is everything, there should be only one everything. So most of us were perfectly happy with the idea that there was one universe. And then along comes this guy and his pictures and all, and then these other people you're going to meet. Very, very smart people, I should tell you, be sitting here on the stage, who believe there is not one, but strangely, as you've just heard, many universes. So their universe gets a plural, gets an S, which is a little odd, you know, and even more nonsensically, really, these people then insist, or propose and insist, or at least artfully describe, many, 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 perhaps an infinite number of universes. And they don't mean, you know, like an idea in your head or a mathematical equation or an abstraction or a logical. No, they are saying, as you just saw, they're saying, no, this is the real deal. We're proposing that there are actual physical universes with energy and matter and maybe atoms and stars and gases and, you know, real stuff actually out there in great, perhaps endless array, and collectively they're calling it the multiverse. So that's the subject tonight. But instead of just insisting that it's true, I'm going to just reset it here because I'm going to, you'll see. So you should know, first of all, this is not everybody's view. David Gross, a Nobel Prize-winning physicist at UC Santa Barbara, very respected man, thinks this is, and these are his words, inelegant, unprovable, and unlikely idea. And there's a guy named, many of you read maybe in Scientific American, the mathematician Martin Gardner, who calls it a frivolous fantasy, intellectually bankrupt. Paul Steinhardt, aforementioned by Brian, the Albert Einstein professor at Princeton, says, I'm quoting him, this is a dangerous idea that I am simply unwilling to contemplate. So, what we're going to talk about tonight is not a consensus view. It is actually highly debatable, but because it's an idea that is rich and important, and I have to confess very important, we loaded the dice, we loaded our stage with universe pluralists, called the S-men because they spell the universe with an S, and they'll be here in a moment. I should confess right off, though, that I am not a scientist. I am not especially learned about these things. I'm here basically understanding for most of you. Wow, because it's my job to say to these folks, what do you mean? What are you talking about? How do you know this? Why do you say that? This is a science festival, not for scientists, but for curious people like yourselves who want to spend an hour or two in the springtime asking what is and what can be known about our universe, or our universe says. So we'll get on with it. I will go to the far seat. And filling in around me will be Nick Bostrom, who is I guess they should just come in as a bunch, maybe. They will be smiling, as Brian predicted. So I don't know. They'll come in eventually. I'll just tell you who they're going to be. Oh, here they are. Okay. Hey, Nick. Okay. So, for purposes, this is Nick Bostrom. He's a philosopher who proposes there's not only many universes, an awful lot of them may be computer simulations. So everything you see about you right now, just touch your leg if you like, feel the garments, feel the texture there. It's not really complete. Nick Bostrom is also director of the Future of Humanity Institute at Oxford University, which will worry you later in the evening. Alan Guth is professor of physics at MIT, world-renowned for his theories of inflationary cosmology. Basically, because of Alan, the story we tell about the universe has changed what he's discovered and what's changed. So that's him. And then Brian is professor of physics and mathematics at Columbia University, author of The Fabric of the Cosmos, The Elegant Universe, made some rather significant discoveries in his field, which is superstring theory, and his ability to explain ridiculously complicated subjects like this one has irritated me, but made him beloved by many. And Andre Linde is a cosmologist and professor of physics at Stanford who believes the universe is endlessly and forever multiplying into more and more and more and more universes. If you want someone to blame for this, blame that man. All right, so let's begin with this. Just to go back over Brian's story, just a couple. I want to just drop in a couple of places. The Big Bang. I want to visit that one more time. You said that there is. Can find evidence such as the microwave radiation. Is that how you also said the universe begins? But how do we know? Just describe it. Like, what happened? Why they call it a big bang? Yeah.
Well, that actually began as a derogatory. I think it was Fred Hoyle, who did not believe in this way of thinking about things in a radio interview. He said, "Oh, those guys are talking about the Big Bang." So it was that kind of a name that he gave to it. And the idea simply is, if you imagine something small and getting bigger, and you try to relate it to the things that you see in the world around you, when things explode, they get bigger. So it's as if there's a cosmic explosion. Now, that way of thinking about things is really awkward, because that almost makes it sound as though there was a surrounding universe within which this Big Bang took place. And that's not typically how we think about it, although when we start the multiverse, it tends to become a little bit more vague. But forgetting about the multiverse for a second, just starting simple, the traditional Big Bang theory envisions that everything is in this tiny nugget that you begin with. There is no external space. And as it grows, it creates the space all around us.
And because space and time, says Einstein, are the same thing, if I asked you, what happened just before the Big Bang? How would you answer that?
Well, there are many questions in cosmology that are very awkward, and that certainly is one of them. And there's no universal answer to that question. When you get to the multiverse picture, the answer shifts. But let's again start simple. In the traditional Big Bang, one way of thinking about it is there is no time before the Big Bang because time and space come into existence with that event. It's as if I said to you, how do you go further north than the North Pole? It doesn't have any meaning, right? North is defined, and that's where it starts. So, if you say, how do you go before the Big Bang, I say it has no meaning. Now, there are other approaches, and we'll discuss them here tonight, where the Big Bang is an interesting event, but it's not the creation event. And there can be, in a sense, events that take place before it.
So do you all sort of just, you all would rather look past what happens before questions and move on? Because I know, by the way, there's a Calvin and Hobbes that's very cool about this. That Calvin says to Hobbes, what kind of this is a cartoon character you should know about a tiger and man. And the boy says to his tiger, why did they come up with that name? Do we have that? Do we have the? Yeah. So if you look over here in this panel here, there's the alternate name, I think, the horrendous space kablooey, or it just might be a better, but I will move on for the second. When you begin, when you have this moment at the beginning, Al, you get a dense soup of stuff, I guess it's very, very hot, and then. And now I want to ask you, there's some problems. Very first instant, and turns into clouds and galaxies like Brian. The universe keeps extending outwards. It doesn't turn into a circle. I need a target. It's something of a plane, so it can expand. And if you look around in all directions, like those radio people did, you find the same how do you explain it? Why do you write an episode book? This idea I just had is a spectacular realization.
Right. Well, that happened one night when I put several things together with real doing over time. But the key idea is this idea of inflation. It really did in the end get me. And what I realized is that, well put together,
I don't have a
good
target.
6 months of prelude, a number of lucky pieces of information fell into my lap during that time. It really was a very lucky find on my part, although I think it certainly would have been discovered by somebody soon, regardless. But the key idea was that I was looking at a phase transition that thought took place in the universe, and I was looking at the idea that the phase transition may have undergone a very significant amount of supercooling, all motivated by studying things called magnetic monopoles.
That's not good.
Let's get into it. Yeah, one. I wasn't going.
Good, good.
Mention the word, I threw it away.
Threw it away.
Just like it was good. Good. But anyway, the supercooling, I realized, following through on some calculations, would produce this peculiar field, essentially what Brian has been alluding to, which would create this repulsive gravitational effect. And it would have enormous consequence for the expansion history of the universe.
Enormous consequence. If the Earth, if the universe is really, really cool, like this, how much does it grow?
Okay, I'm not sure very far away, but the kind of number that I was using then and still seem plausible are 10 to the minus 35 seconds. Incredibly decimal point.
So much faster than.
That's right, much faster than. That's right. You can't do it. You can try, but you're not going to be able to do it.
I won't even try.
And during this time, it expands by a factor of like 10 to the 25.
So 10 with 25 zeros.
That's right. The 1 with 25.
How big does that make it? Like
it goes from a size that's more than 1 billion times smaller than the proton. At the end of this, we envision it as being approximately the size of a marble. Still very small.
a marble?
A marble, right. That's the whole universe right there.
Well, that's puzzling.
Right. Well, it keeps expanding after that,
Oh,
but not accelerating after that.
Oh, so then it just grows more. So
Then it
why
just
did
goes.
this thing stop?
It stopped because the stuff that was pushing it, this field, was unstable. So like the radioactive substance,
So this opposite of gravity, this instead of come to me, this get out of my way, these sharp elbows. Right. If that repulsive thing creates this ping pong ball-sized universe, then how does that solve the problems I just mentioned? How does that make the universe seem flat so it can expand? How does that create the possibility of matter? So there's stars over here. How does that create that sense of sameness?
Okay, let me take them probably the exact opposite. Starting with sameness, that's I think easier. Conventional technology for the early universe found it so high that there really was not enough time to use each other, even if they could send signals to each other at the speed of light. So the conclusion was that the universe could have started out perfectly uniform. We don't really know how it started out. But if it did not start out perfectly uniform, in conventional cosmology, there was never enough time for it to do that. It stayed very long. In fact, the universe, the early universe, is very smooth. The non-uniform is crucially important. They were only at the level of about 1 part in 1,000. 1 part in 100,000 in the early universe was smooth. Inflation can explain that because with this spurt of expansion, it means that before the spurt, the nascent universe was vastly smaller than it would have been in any previous theory. And while it was vastly smaller, there was plenty of time for it to smooth itself out by the same way the air in the room smooths itself out, so that we don't have lots of pockets of hydrogen. It takes a little time for that. But there was enough time on this very small scale. Then this tiny speck, more than 1 billion times smaller than the size of a proton, talk about such things that think we believe in, expands, and it's stretched out by the inflation itself, and becomes large enough to become this marble, which then coasts to become large enough to include literally everything that we see today.
By the way, the marble getting to be literally everything we see today, is that because there's a lot of energy in that little marble, and the energy gradually cools into matter, and then everything's in, so you get more space, more time, more space, more time, and
That's right. That's right. And that latter part is really just coasting.
Okay. So you solve the sameness problem, you solve the clumping
Okay,
problem.
that's the sameness problem.
Yeah.
The clumping problem comes from quantum fluctuations. On the smallest scale, even in this room, we think that we measure things on the scale of atoms. Large fluctuations. see everything. And what inflation does is it takes a very small scale separation.
Itty bitty perturbations become galaxies or huge fields of galaxies.
That's right.
Okay.
That's right.
What was my other one?
And then the last is flatness.
Flatness.
Flatness is a little hard to understand, but let me say that we don't know what shape the universe started out, but one image which makes it simple to picture, and one possibility really, is the universe could have started out essentially round, what we call a closed universe, which is the analog. It's a three-dimensional analog of a sphere. That would be what I'm illustrating with my hands.
Yep.
Whatever number of dimensions you want to count.
Did a good job there.
That's right. You did a good job. Right? It's a two-dimensional surface, but in a three-dimensional space. Right? So the universe could have started out like that. Then inflation basically just makes it vastly larger, and it ends up looking flat for exactly the same reason that the surface of the Earth is flat, even though the Earth is really round. Stretch it out enormously.
Well, let me then go on to the next step. So we have this little thing that's growing into a bigger thing. It clears up some early problems that makes the universe a little more familiar to us. But now my question is called the graceful exit problem. This root form of gravity in reverse and it's pushing everything out. Doesn't seem to just, you said it sort of stops growing, but it doesn't seem to stop growing in a boom. It just keeps on kind of bothering the universe. And it is from this flux of repulsive gravity that we get this. I hope you can see me. Andre, here's my question to you. How do you get from one universe to more than one universe?
Watch, I shall prove it to you.
First of all, let's try to understand how we can get around. Because what Alan did, he suggested an idea how to make the universe big and everything, etc. But then when these bubbles in his universe, when the universe starts this vacuum state, whatever energetic state start decaying, it produces bubbles, bubbles start colliding.
Well, wait, let me stop you there. So there's this energy, and the energy is pushing everything out. And then in Brian's movie, periodically the energy seems to like take a, it seems to just sigh here and there.
Right.
So the energy level goes down here, but not here, but not here. And every time this repulsive energy thing sort of gives up a little space, that's where you get a universe?
Yeah, well, that's how you get an interior of the universe. See, in Alan's picture, you have the universe like this Swiss cheese, and then the bubbles appear, and the bubbles collide. And after they collide, kind of they disappear maybe, but the universe, unfortunately, after that became inhomogeneous. And then I had my own night, like Alan's, except for this was a night when I was, I brought the phone to my restroom because this was the only place in my home where I would not wake my son. So I would call to some of my colleagues, look, I have an idea. That's, is it stupid or not? Because what
Wait, so you had your inspiration, rushed to the bathroom, hid your phone?
Well,
this is a good story.
I had my inspiration a little bit before, but what is important that it did not stop after I went to the restroom. And I went to the restroom, not for the reason you suspect me, but for the reason that I needed to call my colleague to check whether what I'm thinking is stupid or not. Okay? And he said, no, I don't think that it is stupid. And then I wake up.
Wait. So do you have to say something mathematical? Or say, I want to tell you something, do you think I'm crazy? Or do you say,
no, it was strictly mathematical. As mathematical goes with the phone. But anyway, what happens in the end, I just wake up my wife and say, look, it seems that I know how the universe was created. Okay. So,
that's one big trip to the bathroom.
I guess we'll all try later. Anyway, so, but not each time so successful. So here, the idea was this. You have many of these bubbles, but then these bubbles may continue expand internally. And when when you have this boom, when this energy goes down, they still continue expanding, and as a result, you do not see these parts, this wall of the bubble and that wall of the bubble colliding with each other, because the interior grows so large that you do not see the catastrophe. You only get the benefits of internal part expanding. So then you get smooth ending of inflation, this slow roll and everything like that. Smooth ending of inflation inside one balloon.
I'm sorry, I'm going to translate you back to myself. So in my universe, there's a certain logic. Things expand around me and then expand and there's a sort of smoothness to the creation in my universe. But if my universe is over here, the next universe is over there. So I leave my universe in the space between his universe. I'm a bubble, next bubble, and there's space between us going very, very fast. Our universe is mine's okay, his is okay. Look, we're getting, is that what you're saying?
Because if this would be so in the first representation theory, the new universe would be empty. Okay? So what happened is that it is not only that both of the universes are okay, but because of this smooth bump and expansion of yourself, not only of the distance between your and Nick's universe, but what happens around you, then you have a big part of the universe to occupy for yourself. It was like peaceful coexistence. Like I was in Russia, Alan was in the United States. We had that kind of problems. Okay? So now, what if our country, Russia, well, right now in US, expand exponentially, and then US expand exponentially, and just not hurt each other on the boundary, but just expand on all their own resources. That's what we suggested for the universe to do, to peacefully, without this crashing. Okay?
Well, I still don't understand why you could start with one universe, and then get another, and another, and another. There's a missing logic here. I don't quite follow.
Okay, so let me perhaps a better way to show something. This, by the way, this is a picture to which we will return a little bit later. But can you show me the golden universe right now? Yeah, okay. So these are computer simulations. You see, when you want to have high-tech cheating, you go to computer, you do it. So that's what we did. This is X, this is Y on these two axes. See, and this is a laser weapon. And here the height shows you the energy density level in the universe, or the value of the scalar field, or whatever you call it. This is something which is responsible for expansion of the universe. The higher it is, the faster the universe expands. Now, we started the simulation with nearly homogeneous universe, and then the universe started expanding exponentially fast. Computer cannot expand exponentially fast. So each new image is actually showing exponentially larger part of the universe, but just computer shrinks it back. And then these small waves are the following. You see here this inhomogeneous quantum fluctuations. They freeze on top of each other, universe continue expanding, new quantum fluctuations freeze on top of each other, universe continue expanding, and then in some places, well, the universe goes down, the energy level in average goes down, okay? And we live somewhere in this corner or somewhere around where these fluctuations are small, and when they are small, they launch satellite, they see what happens, and they get this strange thing curves, and they see with experimental data. But there are some other parts where these fluctuations add up at each new jump, add up, and they produce other parts of the universe which are so dense, they expand much faster than the original part of the universe. And this is the place where new parts of the universe are created. So you start with tiny patch of space, and then, according to classical theory, which we all love, it would go down and everything would finish. But because of quantum fluctuations, it produces some regions where this expansion continue forever. By the way, this part, the part which shows these small perturbations, this is the one which is called experimentally tested and going to be experimentally tested. Can you show this Planck satellite, this movie, which shows the recent launch of this satellite, Planck satellite. It was launched on 14th of May. It is going to produce data, release data probably in 3 years from now. And it will show these small, colored spots on sky, which are the results of these tiny fluctuations on a small scale. And then in the end of it, after all of these checked, and hopefully will be in agreement with this theory that we have right now, we will have pictures like the one which I would like to show right now. It's a colored universe. Can you show me? So this is the picture which, okay. So here is the universe, which is similar to the first picture, X and Y. And here is the density, but here are different colors. Different colors show that in some part of the universe, you have space with some kind of properties, let's call it red. And in some other part, it's different type of property, let's call it green. And by historical reasons, because I was from Russia, I started with simulations with red square. And then you see everything ends up with the universe which is multicolored. So what does it mean multicolored? Like you have water, okay? Yeah, actually I have water. So water can be solid water, it can be liquid water, it can be gas. Okay? There's the same water, the same chemistry in it, the same physics in it. Same can be with theory. You can have one fundamental theory for everything, but it can represent different parts of the universe with different properties. You can still have red universe, you can have green universe here, blue universe, but because of exponential expansion of the universe, the distance between red and blue will be exponentially large. And if you decide to cross the border, okay, just start moving from the red universe to the blue universe. There will be boundary here, like domain wall, no policeman is necessary, very, very difficult to cross. And if you are stupid enough, and young enough, brave enough, and cross the boundary, you most probably instantly die. Because
Let me stop you before you. I don't want you to die in the exposition here, because this is a. Can I interrupt you just a second? Because we happen to have a carnival. We're very well endowed on this panel. We have this version, and you're now moving into a chapter a little bit one step past where I want to go just yet.
Okay.
So you hold on. You have one too, right? You have. I don't know if you brought it, but do you have a? I need to have a second version of just building the universe. Could you have one?
Well, I mean, this visual that you see here is a more scientific version of the visual that I showed at the end of the remarks that I was making, where each of these different colors is really a different universe. It's a different bubble in this vast expanding substrate within which all the bubbles are sitting. So the idea is that this is the more technical way of indicating that there can be many, many different kinds of universes inside the different bubbles.
So I just still want to get back, because I want to get back to the underlying notion. The underlying notion is that at the bottom of the existence is this fluxy thing. And the fluxy thing is either a robust, get out of here, get out of my way, or a relaxed, sort of less version of the other. And then in some places, the robustness bursts out and you get separation from one universe to you get lots and lots of distance because it moves very fast, one universe from the other. And then the universes themselves come popping out of this underlying repulsive energy that is always there, sometimes up, sometimes up. Is that the general idea? You know how odd and weird that is? I mean, couldn't you have thought of something simpler?
Well, one thing I think is really important to bear in mind, these ideas, when framed in ordinary language, do sound complicated, do sound strange, they're unfamiliar. But if you look at the mathematics behind the versions of these theories that these two gentlemen came up with, it's actually the simplest mathematics that we encounter in many of our physical theories of this sort. It's very, very straightforward, and it does imply, when you look at the math, that indeed, if these theories are correct, that we're embedded in this vast expanding substrate, and that these openings can happen, and what we consider to be the universe is simply one opening of many possible openings in this vast expanding substrate. And the properties can differ from opening to opening.
Interloper!
So every universe
to steal
is
my mana, aren't you?
a psi of this
Here
flux,
then.
and everything
Have a
between
taste.
is a robust separation. doesn't that mean that the universe, if you mix universe and my universe, is this universe going fast?
Really fast.
So the universe, that is, his universe and my universe are getting further and further at beyond the speed of light?
If they're far enough apart, it would be faster than the speed of light, yes.
I think we couldn't go faster.
Einstein only told us that nothing can travel through space faster than the speed of light. He didn't say anything about objects that are being pulled apart by the expansion of space itself. So if objects are sufficiently far apart and space is expanding, their motion relative to one another will, in a sense, be faster than the speed of light, which means that they will be permanently beyond your ability to talk to communicate with. So they are out there, but they are permanently beyond your ability to see or for them to see you.
Before we get to that, so you've just increased, what I would have used to call the universe, you've just increased it enormously. You're doubling at the speed, I mean, it's in...
No, when these guys came on the scene, the picture of the vastness of the universe changed dramatically. There was one time, the universe was like 14 billion years old. It was roughly 14 billion light years across, more or less, if you factor in. But these guys changed it by factors close to the 100. Or infinite.
We should add that it's not a precise or complete picture what we're discussing. Sometimes the universe can crash into it. So
sometimes the universe can what?
Sometimes, you see the domain wall coming on you and crushes you, and you actually do not see it because it moves through the speed of light. So at the moment when it crashes, you start seeing it. And
well, Audrey, let me just readdress it. Why?
Not a problem, I should point out.
Why do you think that this is going? You added the notion that it's going to go on and on and on and on. So do you think there's a beginning to the multiverse, and do you think there's an end to it? Like in any one of these universes, I think you could get exhausted and die, and the universe could collapse. But this big thing doesn't seem to have a collapse in it. So is it an eternal universe you are proposing?
To the future.
If we can show again this bubbly universe in the picture. Okay, so as for the beginning, as Alan together with several other people have shown, we still need this, something that we are screening probably by our here, this first bubble appearing here. There probably must be something which started the whole tree growing. Maybe, however, it did not start simultaneously in the whole universe. But what happens once this process of producing new universe starts, it never ends. So the universe is eternal in the future. So what does it mean for us? Well, some things. Like, for example, previously we thought that this first bubble, which is partially screened by the chairs, first bubble is the whole thing. What we wanted to explain, cosmology wanted to explain, we see the universe around us. It's more or less homogeneous in more or less uniform direction. In fact, Albert Einstein had the idea that the universe must be uniform. Some other people called it cosmological principle. We can still see it in the books of astrophysics. Perfect cosmological principle means that the universe must be uniform. So if it is yellow balloon, this is yellow balloon. And sometimes I used to make a joke that some people who don't have good ideas, they have principles. So, but I stopped making this joke after I learned that this cosmological principle was invented by Albert Einstein.
I need to target
simply
first.
Well, so what happens here? Greeks had this idea of perfect sphere. We wanted to have some mechanism which explains why our universe is a perfect sphere. And then inflation explains why our universe locally looks like a sphere, but then inflation told you that the universe globally looks like a fractal, eternally growing fractal. So what was the leading idea of Greeks? Perfect sphere. What was the beauty concept of 20th century is a fractal. And that's exactly what inflationary theory brought to you. The multiverse as a fractal, and fractal having all possible colors.
Why won't it stop?
It would not. It is continue growing, producing new and new. Like, look,
But
suppose
why? Is this because that? Why?
Try, I'm sure you can. One way of thinking about this Zoomps, it falls down, but the part that hasn't fallen down continues to grow. So you've got a growing effect. You've got more and more of the stuff that's pushing outwards, created every moment, and only some of it is falling down. So some falls down, but some gets larger, and the amount that it grows larger always, in these models, beats out the amount that falls down. So there's always some place out there filled with this stuff that does that.
So it just goes on. Now wait, if
reproduces.
I live in this universe, and this universe, this one here, let's say it's ours, so it has, you know, the physics of ours. It has gravity, and it has atoms, and it has forces. And then I think about this universe. Does this universe have the same gravity that we have and the same atoms we have? Do you know? Do you have a theory?
No, that's why it is blue. Okay?
Oh! Oh, you're a mean man. So therefore, there are not only many, many, many universes, but there are many, many, many kinds of universes?
Yeah, and you know how many? Okay, well, things like in 80-something, 86, 87, people working in stringy community speculated how many, and they said it's probably 10 to the degree 1,000 different universes.
Different kinds?
Yes, but nobody took them seriously, okay? Because they did not have any one demonstrably, well, whatever, probably existing which would be, well, stable, kind of. You see, string theory is based on the idea that our space fundamentally is 10-dimensional, maybe. And then 6 of these 10 dimensions are squeezed into something very, very small, and 4 are large, like 3 space and 1 time. Okay? But nobody was able to actually keep these 6 dimensions from starting expanding. The universe wanted to be 10-dimensional. And something happened in, well, 2003. Several people from Stanford, well, I was a cosmology consultant there. There was Kachru, Kalash, and Trivedi from India. They've suggested some mechanism how to stabilize these 6 dimensions. Can you show Calabi-Yau picture? Here. Well, this is, well, some mathematician actually produced an image of how the 6-dimensional space looks like. Okay? So 6-dimensional space is compactified, but it can be compactified in so many different ways. It has so many different holes, and because there are lots of combinatorial freedom there, the total number of ways it can compactify is exponentially large. And for each type of this way, we have different properties of our universe. Different properties of elementary particle physics, different energy of empty space, different everything. And when people calculated the number of these stable compactifications, they came to the number 10 to the degree 500.
10 to the degree 500.
This means 10, and okay, so it is like 1 and 500 zeros there, right? Okay, approximately. It's plus minus something to the way. At some moment they start saying, actually maybe there will be infinitely many, but then they cut back to the standard.
Wait, stop for a second. You have to take a breath with you. All right, so I haven't asked you anything yet. Hi. Does it strike you as a little difficult? That is open to everything. I mean, wouldn't a theory be a good theory? Let me just say, I have a line here somewhere. A good theory.
Better be a good line.
Yeah. Well, I don't remember where it is, but
yeah, you see, you have nothing against it. After all.
It seems to me that a theory that says that anything is possible doesn't explain anything. I mean, a good theory says why this is so. But that this multiverse contains just about every conceivable, including that weirdly shaped thing that was behind it, every conceivable organization of matter, every conceivable number of dimensions, every conceivable possibility. And I say, well, okay, if that's your idea of science, then go ahead and conceive in the bathroom again, because that's not. How do you, I mean, if it's too much. Well, I'm just interested in your opinion.
No, it's
you get a similar problem even if you just have one universe. It's big enough. Say it's infinite, you will have all possible types of observers in the center, and having all possible types of illusions. So whatever measurements you make, even in a single instance, you will have some observer somewhere. Now imagining that they're making a type of illusion. The question then becomes, how can you test theories if all the theories you're comparing need to predict that for any possible observation you make, there will be some observation. It seems that the theories are consistent with all possible observations. So this is the problem. And the solution must be to consider not just whether a theory says that a given observation will be made, but what the theory says about the frequency with which these types of observations will be made. So you have to think about if there are all possible types of observers making all possible types of observations. The interesting thing is, what will most observers see in a given type of universe? So you think about the fraction of observers who will make the particular type of
Let me ask
observation.
that question in a different way to you, to all of you. This universe that we're in seems to have a very, very sensitive sort of set of circumstances. So our gravity is just so. The forces that bind atoms are just so. And if you changed any of those variables, and I think there's 6 or 10 or some very important ones, then the universe as we know it would collapse and we wouldn't be here. So people sometimes ask, as you I guess just did, like how many of them, of all of the universes, are like our universes where life is possible and intelligent life is possible, and how many of them are, and how come we're in ours? Are we in ours because we just are here at the end result of a set of circumstances, or are we in ours because somehow our universe expected us?
Well, I mean, one way of thinking about this that comes out of these pictures, I mean, if you have, Andre's image of all the different universes in different colors, if we can only exist in a red universe, then if you ask yourself, why are we in a red universe? We're there because we can live there. I mean, this is the kind of reasoning that we accept in other circumstances. If I said to you, why do we live on the surface of a planet? Why don't we live in interstellar space? The answer is pretty clear. We couldn't survive in interstellar space.
Did that dragon send you into the
life? That's why we're here. Similarly, why are we in this universe? Well, we're here because
we'll all meet for a meeting of honor.
This may feel somewhat circular, tautological, but what gives us power is when you really start to realize that if that picture's true and there really are these other things out there, it's not just mathematics, it's real, then of course we're going to be in the one that we can live in. And that is a reasonable explanation, if indeed this picture is correct.
How do you guys know that Andre's probably right? How do you know the answer to your question? Like how do we know that we can't see them? They're receding further and further away faster than the speed of light. So how do we answer the question? There's no crow that can fly over the whole thing.
I think it would be too strong to say that we can know at this point that Andre is right. But one of the reasons for taking this type of model seriously is exactly this problem that you mentioned, the fine-tuning problem. So we see that there are a number of these physical constants that appear to be possible. Why should I have exactly the right values that enable, human beings or enable any kind of complex chemistry at all?
And I wasn't even cool enough to tell. I should have told that story much more dramatically. That's really,
it's really precise fine-tuning, and there are sort of 4 different possible approaches you can take to this. It could be just a coincidence, but by definition, it would be very unlikely that the values would just turn out right by chance. Of course, if you're religious, you could think that God designed it to be like this, but that explanation has all sorts of other problems that are well known. Okay. You could search.
What are you doing?
You could search for some simple underlying
You may be
theory.
hit by lightning.
Well, okay. Well, you could search for some further simple theory that nobody has thought of, some simple equation that is itself very simple, but from which all these specific values of the constants just pop out. Problem is nobody has any idea of what that would be. And the 4th path, which is the one that Linde and Guth et al. Are exploring, is that there is this big ensemble of universes, and the values of constants in these universes vary randomly. So when you have all or almost all possible different constellations of values of these constancies are implemented or instantiated in some universe or another. But most of these possible universes will be void of observers. The observers will only live in those universes where the values are exactly right for the evolution and existence of life, complex chemistry. So all observers will find themselves living in these universes where the values look like they are just fine-tuned, because they only see the universes where they are fine-tuned. All the others are void of observers, or at least there are much fewer observers. And so that would then explain the appearance of fine-tuning, and the fact that you could explain that through this kind of multiverse theory is one of the underlying rationales for taking this kind of
So
theory
you've just,
seriously.
therefore, you've created a vast array of different kind of universes. You've conveniently gotten rid of God and be a random upsurge. But you haven't gotten rid of the mysterious fact that you all hold on to, which is underlying this whole system, is still this flux, this gravity that is that's pushing out and sighing and pushing out. This gravity has become a godlike omnipotent. Why do you all think that this is to be assumed? That's an assumption just like any first assumption, and you're stuck with it.
No. The thing that we're reporting is the simplest model, and that's why the gravity is you. Of course, you can do more better, but this will be, well, reserved for the next, I guess, meeting here. But right now we are trying to do the simplest job. So what we have shown you, assuming some fundamental laws of physics, including gravity and what happens there, and you already have 10 to the 500 different possibilities. So that's just the simplest.
So you're not worried you have to assume a underlying but universal set of gravitational law?
It's self-constraining rule. It's, you know, probably I should say something psychological. Okay. Like when I was living in Russia, okay, we had one particular rule, and we knew that it was right and the only possible. And eventually we will spread it. And therefore, when we have freedom, having 10 to the 500 different possibilities, and I'm coming to the country which has freedom, and suddenly, oh, it's too much of it. This is 10 to the 500. We need one rule. I say, my God, what is going on?
So he's comfortable with freedom. What about you, Brian?
Well, the criticism that you make, I think, can be made always. You're always, when you're a theorist, putting forward ideas, and even if they're successful, you can say, well, why those ideas? I think that that's an issue that can always be raised. I don't think it's one that we can really deal with. But speaking from my perspective as a string theorist, let me just say why I find these ideas compelling. And it's really what Andre was describing. When these guys developed these cosmologies, there would be all these different bubble universes out there. That was a very interesting cosmology. Put that to the side for a moment. We're working on string theory for all these years. And indeed, there's this feature string theory that you have more than 3 dimensions in space. You have 6, possibly 7 other dimensions in space that, as Andre was saying, the lost picture can be curled up into little tiny spaces. And our hope in the 80s was that there would be one particular shape for the extra dimension. That if we knew it, we'd be able to then explain all of the observed features of the world around us. It turns out, the size and shape of those extra dimensions is determined things like the electrons, the mass of the quark, the strength of the force. We had this image that one day we're going to understand which shape there is for the extra dimensions, we'll calculate everything, and we'll all agree, and it's done. The more we went on, we found more and more shapes for the extra dimensions. We had a catalog of a few hundred in the 80s. It went up to a few thousand in the 90s, and it just blossomed into, as Andre was saying, 10 to the 500 different possible shapes of the extra dimensions. You're like, wow, this is turning out not to be the way that we thought it was going to go. Then when you take a look at the cosmological picture, it's very interesting. You get 10 to the 500 shapes to realize all of these different bubbles, and when you have that picture, then the explanation for why things are the way they are becomes far simpler. We see things to be the way they are because we can exist in that particular bubble with that shape of the extra that's compatible with our biology and our chemistry.
So describe the biggest bribe.
Biggest what?
The biggest bribe.
Oh, what was that?
Oh, okay. So So here what happened. In 98, people have found, cosmologists have found that there is vacuum energy. Empty space is not entirely empty. Not empty. And it shows in exponential expansion of the universe right now. The universe, But the fact is that when string theorists learned about it, Ed Whitman, who is, well, the head of the string, there is one of the
He's very,
leaders.
very, very esteemed.
Okay.
Look,
one of the
they're
major
headed for
leaders
grandfather's
in
pool.
string theory mentioned in his talk in India that I do not know
It's not too
how
late.
string
We'll just
theory
jump the
can
mountains to
explain
cut them off and...
And when he said so, Ed doesn't know.
No,
And
no, they're
I also
everywhere.
don't know. Nobody knows. And then what is going on? String theory does not know how to describe our universe. So
Hang on.
that was bad.
We're going
and then
in low.
everybody started being nervous, and I start checking how to describe it. And then finally we have found a way how to describe it. And then we found this 10 to the 5 ways to describe it. But then the thing was that the value of vacuum energy, which people experimentally found, was absolutely incredibly minuscule. It was 10 to the degree minus 120 of expected value. See, theorists have calculated. If it is non-zero, what will be the next number? Okay, so the next number was huge, and people experimentally found something which is 10 to the minus 120 of this, which means 0 point, and then 120 zeros, and then 1 standing there. And it looked absolutely ridiculous. Okay? So, however, now we have this 10 to the 500 states. Okay, so now watch. Here, this is theoretically expected value. Okay, this is 0, and this is another, well, negative theoretically expected value. Now let's slice it by these slices. 10 to the 500 different slices. Okay. Then you come close to 0. You come to the place where it is 10 to the minus 120. See? So it is still, you continue slicing because there are 10 to the 500 slices. So in this tiny place, 10 to the minus 120, you have 10 to the plus 380 slices. Different types of the universes with a cosmological constant which just fits experimental data. Okay? So first...
I don't know what you just said, but it came out good in the end, didn't it?
Okay. So string theory allows to describe the universe with this tiny, tiny value of vacuum energy. But then the second step, if vacuum energy was just 100 times larger, okay, or if it is negative and 100 times larger but negative, we would not be able to live there. That's the proper principle says, okay? Because why? If we're here, then the galaxies would be torn apart. If we're here, down below, then the universe will collapse too quickly for this, well, discussion to take place. Okay, so what we have found that string theory allows to explain this value of vacuum energy, and so far no other explanation was proposed.
Oh, here we go. So your ultimate defense is that the only explanation that just might cover the situation is this one, which we can't test, but it's the one maybe left standing just so in the middle of the
String theory plus inflationary theory together give you the only explanation of the experiment which was happened 10 years ago. So far, nobody suggested anything.
I don't have a
But
target.
see, if that's your defense, that we've got the best explanation, here's a review of that explanation by somebody named Bryce DeWitt. You know who he's important to me. Bryce DeWitt. I go where I must. I don't even know who I'm quoting.
I need to target something.
I still recall vividly the shock I experienced first encountering the multi-world concept. The idea of 10 to 100 plus slightly imperfect copies of oneself, all splitting into more and more copies, is not easy to reconcile with common sense. This is schizophrenia with a vengeance. Signed Bryce DeWitt. Martin Gardner, the mathematician. In my layman's opinion, these are frivolous fantasies. Surely the conjecture that just one universe with one creator is infinitely simpler and easier to believe that there are countless billions upon billions of worlds constantly increasing in number and created by nobody. John Wheeler, Mr. Uno, who we all bow down to apparently, says, I don't know, I'm turning against it. It contains too much physical baggage. And John S. Bell, a physicist from Ireland, says this is just plain silly. Well,
so Robert, I should just jump in. One thing that we haven't emphasized too much tonight is that there are many flavors of parallel universes. We've been focusing on the one that comes out of inflationary cosmology. Most of the comments that you're referring to there are coming at the version of many worlds from quantum mechanical version of world physics, which is another flavor of the way that you can get power. It's rather different from the one that we've been talking about today.
Maybe I did not fail.
No, but there is a criticism that certainly can be launched. It does feel uneconomical when you hear about all these other universes. But I have to agree with Andre. I certainly had the perspective in the 80s and 90s that there's one universe, we're going to work out the laws, we'll have some unique predictions, and we'll be kind of done. That was certainly my perspective. And when this experiment in 1998 took place that Andre was referring to, which found that the universe is accelerating in its expansion, which means there's some more of that pushing out stuff out there today, and the amount of that dark energy, as we call it, is this fantastically small number, about 10 to the minus 120, we say to ourselves, can we envision ever doing a calculation, starting with some interesting equations and pi's and e's and square roots of 2, the kinds of things that appear in a natural calculation, and by the end of the calculation, the answer to be 0.000000120, and none of us can imagine that we'll ever do a calculation where that is the answer. We look for other ways of getting to that result. One of the other ways is, if there are many, many universes where this amount of dark energy varies from one to another, there's going to be at least one. There are enough universes out there where it has a small value that we see. I mean, it's as if I have a deck of cards, and I randomly take one, and I throw a few cards out, it's unlikely that someone's going to get the ace of spades if I just throw a few cards. But if I have, this is a room of about 900 people, if I have 900 cards, take many decks, and I just throw them all out there, I'm sure someone's going to have an ace of spades. But somewhere, in fact, there are a few aces of spades if we've got 900 cards.
So you've just described, say, the event of us. The reason we're just one of those many.
We're just the ace of spades out there, and it's hard for us to envision doing a calculation in a unique universe where we get that crazy small number.
But you're supposed to. So, as scientists, aren't you supposed to try to find some way to examine your theory?
Oh,
if the universe that you want to check ours
need to get closer.
is rushing at more than the speed of light in some other direction, how will you ever...
That's a great question, but one thing that is worth emphasizing too, you described these bubbles.
That's a great question.
No, I really do. I really do. So we've been describing these different universes are rushing apart really quickly, and that's sort of the generic case. But if two of these bubbles are really close when they're created, they can slam into each other. And if they do slam into each other, this could leave little ripples on this radiation that we were been talking about, this microwave background radiation. So there are people looking for these ripples, and that could really give evidence that we were slammed into by one of these other bubble universes. So it's not that it's completely beyond the ability to test this idea.
Let me stick in one more idea here. People are sort of used to the idea that there ought to be one universe. We're talking about many, it seems like it's very fancy. But let's think about it, really. If we think of all the nouns in the English language, all the nouns you can find in the dictionary, how many of them are there just one of? Or does anybody anticipate the idea that there might be just one of? I know of only 2 nouns that could fit that bill, and that is God and universe. So if you want to have a scientific concept of the universe...
I'm so wishing I could come up with something.
If you want to have a scientific concept of the universe, you want to put it in the same category as God or the same category as planet, galaxy, hospital galaxies, etc.
If you want to be unsettled, then let's go to the silent next, because his idea is galaxy must be God. And I don't know how comfortable you'll be.
I'm not sure I want to claim that honorable position.
So, the thing is called the problem of what is called the simulation argument. So I'll sum up and you explain that it believe that it would be possible for a universe to be simply a staggeringly successful computer that imagines a universe that have an experience that seemed utterly real. So I could go, I would feel my skin and I'd feel the texture of your head. And this would all be, there might be some civilization could build a machine.
Right. So a lot of people have proposed that as a possibility. The whole premise of Matrix or anything like that is that just as we can build simple virtual reality today with simple simulated creatures living inside them, maybe in the future with vastly more powerful computers, we could build more complex virtual reality, more complex simulated creatures. Maybe these creatures could be complex enough that they would actually have brains like ours simulated down to the level of individual neurons and synapses, such that the inhabitants of these simulations are conscious. But what the simulation argument adds to that is that instead of just stopping at the question of how could you ever prove with certainty that we're not in a simulation ourselves, the simulation argument tries to establish a constraint about what we can believe, and it tries to show that one of three possibilities is true, though it doesn't tell us which one it is. Now, in a sense, this sounds more radical even perhaps than some of the multiverse theories that we've heard, but in another sense, it's less because it doesn't presuppose any unknown physics. So we're just assuming that it will be possible to build computers that are much more powerful in the future.
I mean, I think they could be very powerful, but if I thought I was in a computer simulation, I would watch your face really closely because maybe there'd be a skipped frame and you go, and I'd notice that.
Okay. So we can come back to that. I mean, so I get these people writing to me, and anyway. So what the simulation argument tries to show is that one of three possibilities is true. The first one is that almost all civilizations at our stage of technological development go extinct before they become technologically mature. Technologically mature meaning having developed all those technologies we can currently show are physically possible, given only uncontroversially obtainable physics.
So they make a radio, they make a rocket ship, they make a bomb.
Yeah, you could build big computers the size of planets and stuff. We can calculate what performance they would have. We can't build them now, but maybe 1,000 years from now, people will build them. So first possibility is people at our stage, they just fail to get through to that level of technological maturity. Maybe they destroy themselves on the way. Second possibility is that almost all civilizations that do reach technological maturity lose interest in creating these kinds of ancestor simulations, as I call them. These would be detailed computer simulations of people like their historical predecessors. So they have these powerful computers, they have the ability to program them, but they have better things to do with their computers at their time.
Okay, here comes three.
Right, and the third possibility is that we are almost certainly living in a computer simulation. And the argument, in its full version, it requires some probability theory, but the gist of it can be grasped quite simply and intuitively. So if you imagine that the first two possibilities do not obtain, that means some non-negligible fraction of civilizations at our stage do reach technological maturity. Some non-negligible fraction of those are interested in creating these ancestor simulations. They devote some non-trivial fraction of the resources to this end. You can then show that there would be many, many more ancestor simulations than there would be original courses of history. Because
why would there be more simulations?
Because if you calculate the computing power that a technologically mature civilization would have, and the computing power that would be required to simulate all human brains, it turns out that the latter quantity is a tiny, tiny fraction of performance. So, in other words, by devoting a tiny fraction of their computational resources to this end, they could create astronomical numbers, billions and billions and billions.
So you're saying that if the assignment in Mrs. Maggetti's class in the planet Xantar in another universe is, all right, everybody, I want you to make a universe with extraordinary accuracy, and I want you to create 1 billion people with every neuron in place so they all think they're alive. Everybody go. And then Johnny says, can I do it with real matter? Can I make it with like energy and math? No, Johnny, that's 50 tons of stuff. We're just going to do this with bits and bytes. So everybody in the class does it with bits and bytes. And then in the next year, people just keep hitting the repeat button.
Right,
So
so
the
if-
cost of making a pretend universe is just infinitely smaller than making a real one?
Well, maybe not infinitely, but a lot smaller. I mean, to the point where if you have the ability to use advanced form of nanotechnology to transform planets into computational systems, by using just one planetary computer, just a millionth of its computing power for a tiny fraction of 1 second, you could run many, many courses of, simulations of human history.
So if Johnny goes beep, 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 beep,
Well-
beep, 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 that means that creates the likelihood that we're in one of those universes.
Well,
right?
or maybe Johnny just does one, but maybe there are other people millions of years later that repeat it. Over time, there would be more simulations.
How do you wake up in the morning?
Well, so to conclude the little arc of the argument, so if you assume that the first...
You have to. That's the end.
If the first two are false, the first two assumptions, you then reach this conclusion that there would be many more simulations than original. And if almost all people with our types of experiences were simulated rather than implemented in basic level reality, we should think that we are probably one of the typical people, the simulated ones, rather than the very exceptional ones that were part of the original history. So now this doesn't show that we are in a
when you
computer
thought
simulation.
up this idea and you proposed to yourself that maybe it'd be more likely that we're all simulated.
Well,
than
except
real.
that I don't believe
you don't
that.
believe this?
No. So I think that, well, I believe the simulation argument, which shows that one of those three is true, but it doesn't tell us which one. So I think we should distribute our credence over each of these three possibilities. Just don't have enough evidence to pick one. That's what I believe. Now, so as to why if we assume for the sake of the argument that it's the third possibility, the simulation hypothesis, that's true, then a lot of people's first reaction is, well, we might just as well go crazy, anything could happen. But once you start to reflect on it for a while, you realize that even if we are in a simulation, the best way to predict what will happen next, to decide what to do, are still the methods that we would use anyway. We observe patterns in our simulated reality, we extrapolate them, and act accordingly. So the implications are not quite as radical as they might at first be.
Well, I don't. I have to. You're getting up on it.
It depends on when we're.
Okay, because I don't know whether I don't see anybody going like stop. So good. Then collectively,
It's a morning in China.
do you guys feel that a multiverse concept in which there is this array of possibilities, including this rather that you align, if you think of the universe or the many universe in this way, do you feel that it's beautiful, or do you feel that it's to use the Copernican principle notion, that it makes us much smaller, perhaps not even real?
Oh, well, I mean, yeah.
I mean, that it's a very diminished state you have left us in, I think. This idea that you're so... I liked it better with one because, you stood taller in that concept.
Oh, I mean, there are many ways of looking at it, but I've always felt that every time we get diminished, the universe does become more beautiful. And what I mean by that is, it's spectacular to me that we little creatures that are not special systems, we're not sentient creatures, we might actually just be a simulation, yet we figure so much out. So to me, the disparity between sort of how we are and the grandeur of what there is, the more space there is between the two, the more spectacular our understanding becomes. So I don't really feel diminished by it. I really feel energized by all of these things. So, and also I think our aesthetics really is developed and progresses along what we find to be true. There are many things today that I think if you asked, people 500 years ago, what do you think about this idea, it would be foreign and strange and off-putting. But yet, now we've become used to it and our aesthetics have come along for the ride and we now think that these theories are beautiful. So the bottom line is, I think we just have to wait and see if there's evidence for this, or if we can come up with better explanations for the things that currently only have a good explanation in this framework.
Well, let me ask the question in reverse. People sometimes who leave Manhattan and go to Shanghai find Shanghai is so big and so bustly and so overwhelming that when they come back to Times Square, it looks a little bit petite to them. They feel that New York is somehow shrunk around them. Let's do it by the universe. Since you guys have all imagined a multiverse so grand and so Shanghai-ish, does the universe that you live in seem a little bit petite
Well, okay.
We're getting towards the back end of the show, so I'm just throwing them all out here.
I mean, so to be, I mean, even if you have a single universe, if it's infinite, you already have, you know, as much vastness as you could possibly hope for and more. Now, if you then add other universes, it has perhaps interesting observational consequences. But if it's the mere size that you're interested in, you already get that with standard Big Bang cosmology if you have an open universe.
I didn't think that I was wrong. Okay. Well, did you? No. Did you read Bhagavad Gita? I'm sorry. Okay. So one of the famous books of Mahabharata, Bhagavad Gita, and there, there is a story of some famous warrior. He actually he speaks with Krishna, and he asked Krishna, "Can you show me a universal form?" And I don't know. But please, oh please, show me your universal form. And at some moment, Krishna, okay. So he suddenly shown his universal form, and that is the God who eats everything and destroys everything and gives gifts to everything. And he is also a lion, and he is also a tiger, and he is also an elephant, and he is everything, and the waves involved. And then the Arjuna was speaking, "No, please, oh please, show me your normal face." Okay, so this is right now the situation. Just nature is much richer than what we previously thought about. But each step when we learn more, it is more beautiful. It's actually absolutely exciting. It's exhilarating. You're trying to find it all. And then, yes, when you look at it, it's some kind of dangerous. You look at the face of it. You do not understand what it is. No. Let me do something else. Let me do something. So many people go to finance.
But that didn't work out for them.
See? That's why inflation in our theory is much better.
I can't think of a better way to end this thing than right there. I want to thank all of you for participating. If you have a final word, feel free, but I think that was pretty good. So thank you all for coming, and thank you.
It's 8 o'clock. Do you know where your universe is? Start by imagining a tropical lagoon.
This hunger is
To the fish that live near this watery world is all there is. This lagoon is their entire universe. They have no idea there's anything beyond. Well, they are fish. And that theirs is actually just one of a huge number of bodies of water on Earth's surface. Some like theirs, and some very different.
Perhaps it is time to say goodbye.
So now that you are a fish, what if you got a clue that this world of ours is just a tiny lagoon, something much bigger? Would your fish brain handle that?
Means something.
We humans always assumed our universe is one of a kind, unique. Even the word universe reflects this. We think that one and only universe came into existence nearly 14 billion years ago, what's called the Big Bang. In the 1980s, a group of young physicists, including Andre Linde, Paul Steinhardt, Andreas Albrecht, and Alan Guth, came up with an enhanced version of the Big Bang theory. They proposed that in the first instant after the Big Bang, the universe underwent a burst of incredibly rapid expansion called inflation. And satellite measurements of the heat left over from the Big Bang now support the idea. But surprisingly, the theory of inflation also suggested something very odd. According to inflation, the Big Bang that created our universe may not have been a one-time event. Instead, it could have happened again, and again, and again.
Yes,
an
yes.
infinite number of times.
Surrender your power, dragon. These pools
And
belong
just as
to the
our Big
Nightborn
Bang
now.
created our universe, each of those Big Bangs would have created other universes. A process that would continue eternally. So Guth, Linde, and others concluded that instead of a universe, we might be living in a multiverse. The math shows, it's always the math, right, that the multiverse would contain a huge variety of universes, ranging from some that are nothing like ours to others with duplicates of Earth and each and every one of us. In fact, the existence of so many other universes would mean everything that can happen will happen in one universe or another. It's an intriguing, out-of-the-pond idea, but also controversial, igniting a fierce debate in the scientific community. Several scientists, including some who helped create the theory of inflation, come up with counter-arguments to the multiverse. A theory that predicts everything predicts nothing, one wrote. And critics object to considering the multiverse is more akin to philosophy than science. But who's right about the multiverse? We all know how our fishtail would turn out if those fish could find a way to see beyond their doom. They would discover that their universe is not unique, and that Earth's surface is covered with lagoons, ponds, lakes, seas, and oceans, speaking their kind of creatures. This discovery would forever change their picture of reality. But what about us? What would it mean to find we're part of a much larger multiverse? How seriously should we take this idea? And what if I just zapped out of this 2D multiverse and appeared before you right now?
Welcome to the World Science Festival Multiverse Big Idea, or Brian tried to kind of warn us, didn't he, that this get preheated? Maybe I should just completely change my introduction and think maybe just to get us all ready. Welcome to 2013 WrestleMania Cosmology. Are you ready to rumble? Something like that. I mean, that is why you bought tickets, right? But seriously, is the multiverse idea something that's implied by deficiencies in existing cosmological theories? Or is it something some scientists need to help them explain certain unresolvable problems in existing theory? Basically, we are dumped down here in the middle of the incompleteness of cosmology right now, and our mission is to move from stuff we know to stuff we really don't know and take you all along on this journey. But let me just say that in a parallel universe where the Knicks are still in the playoffs, where President Romney closed Gitmo, where David Petraeus did not have an affair, and Margaret Thatcher is still Prime Minister of Britain, yes, it would be a very different world than we see today. Are all probabilities possible, and do they exist simultaneously in multiple universes? Well, I guess if that was the case, there would be no Las Vegas, right? They need it to turn out one way and not the other. We have an extraordinary group of individuals to talk about all of this from the standpoint of very particular positions that will be argued here on this stage, and also from the standpoint of teaching you how this argument is actually playing out with as much of the real physics as we can provide to you all. I'm going to just sit back and let them talk. Please welcome onto our stage, Andre Linde. Studied physics at the Moscow State University. In 1975, he started his work at the Lebedev Physical Institute. In 1985, he became a professor of physics. In 1989, he joined the theory division at CERN, Switzerland. And in 1990, he became a professor of physics at Stanford University. Also, please welcome Alan Guth. Professor of physics at MIT, world-renowned for his discovery of inflationary cosmology, the dominant cosmological paradigm for over 2 decades. His current research focuses on developing mathematical tools for quantitatively analyzing inflation's suggestion that there are an infinite number of universes. And now, Andreas Albrecht. The discovery of cosmic acceleration has been transformative to the field of cosmology. Albrecht is known for his groundbreaking work on dark energy theory and phenomenology. Albrecht moved from a professorship at Imperial College in London to UC Davis in 1998, built the cosmology program there. He's now physics department chair at UC Davis, is a fellow of both the American Physical Society and the Institute of Physics. And finally, Neil Turok. After his PhD at Imperial College in London, Turok was associate scientist at Fermilab, professor of physics at Princeton, chair of mathematical physics in Cambridge. He's now director and Niels Bohr chair at the Perimeter Institute for Theoretical Physics in Ontario, Canada. Please, an applause for all of our panelists. I love that name first and then welcome you on. It does have a kind of a WrestleMania feel to it. I think that's let's start with you, Neil. We begin with what we know. The Big Bang is something that was controversial when I was growing up in the 60s, but is something that's a fairly settled question right now.
It is for most of us, and maybe the way to begin this evening is by emphasizing that the 4 of us agree on far more than we disagree on, in fact. Of course, what we're always interested in are the questions on the frontier of what we know. But over the last 3 decades, we have learned an amazing amount about the universe, and the vast majority of that we can all agree on. We have learned to believe in the Big Bang from many lines of evidence. We are fairly confident that around 14 billion years ago, the universe started out in what I call a ball of light, a very intensely hot piece of energy and radiation about 1 millimeter across, which was expanding with enormous speed. And its space was expanding. It wasn't a bang. In fact, the name is a misnomer. It's big expansion. You have this tiny object which literally expanded into everything we see today. And so the fundamental, here it is on the left, the ball of light expanded, this radiation filling it, cooled, out of that emerged the particles.
It's too far away.
Nuclei, then those nuclei clump together with electrons to form atoms, and the atoms clump together to form galaxies, stars, and planets, and all the things we see today. And so the big mystery of cosmology is the second mystery, which is highlighted recently, is what's going to happen in the future. And here the story is equally mysterious, because that space is not empty. The space between galaxies is not empty. We know it's full of energy, which we call dark energy. This has an effect of causing the expansion to accelerate. So we see the universe now accelerating its expansion, emptying out. The future looks to be very dark, cold, and isolated. So this is
Really?
what...
That's great to hear.
Yeah. So we have this picture of the universe with tons of data reinforcing it, and some very fundamental mysteries. One of the most interesting is that all of light wasn't variations at a level of about 1 part per 1,000. The question is, where did those variations come from? They're incredibly important because those variations later clump into galaxies and stars. They were our and you see in the picture at the top, Planck satellite, just in the last couple of months, released its maps showing us a picture of what those variations look like just when the radiation from the hot plasma of the early universe was released to us about 400,000 years ago. So we are seeing, we believe, the ripple of that tiny ball of light as the universe evolves. The other side is we've learned a lot last year. It's full of Higgs fields. Space is not empty, not just because of dark energy that fills it, but it's also full of this Higgs field which controls the masses of the particles we are made of. And so that's, we've learned this fact, and it's very intriguing. This is all about multiverse. I haven't mentioned multiple universe. And initially I was hoping this format would be much more of a debate, and I hope it will be, because trying to explain this has encouraged theorists to build models. And literally the last 30 years have delivered us at theoretical models. And the multiverse is certainly in our minds, okay? Whether it's in reality is, for me, a very open question. What I would say is that the evidence from last year, the Large Hadron Collider discovering the Higgs boson, goes strongly against the multiverse. Instead, most theorists were expecting more than one Higgs boson, lots of other particles, lots of complications. Instead, the Large Hadron Collider found just one Higgs boson with amazingly simple properties. Properties which indicate that perhaps we can trace
I don't have a
all the way
target.
back to the singularity itself. They point to extraordinary secrets. Likewise, it's showing us simpler than the inflationary model when predicted. Inflation isn't really good. Vast majority of those things ruled out by the data. So I would say the universe made a glimpse of extraordinary simplicity, beauty, and structure. What we need now are theories, principles, mathematics, which explains the simplicity we see. The multiverse is all-brain information. It's a bunch of...
All right, let's hold on for 1 second. You said, let me just ask you a question, and we'll get to the other stories here in a moment. You said that the Planck satellite gives us a picture of something that happened 400,000 years ago?
We can see it as it was 400,000 years ago.
400,000 seems like a blink. Seems like a blink of time, 400,000.
Earlier than that...
Yeah, you said that.
Sorry. Sorry.
I sense the fact here. Yes, I sense the fact. So I just wanted to clarify.
Sorry. Since the back.
Since the Bang.
Bang.
If the Big Bang only happened 400,000 years ago, that would be a big news story.
Yeah.
I would be covering that.
Since the back.
Yeah. Okay. All right.
Since the back. Sorry.
You anticipated the next segment of our program, and that is inflation theory, which while perhaps less generally accepted than the Big Bang, is also embraced by a lot of scientists who are concerned about how the look of the universe that we see now is not explained solely by a Big Bang that expanded continuously. There would have to be a period of time of rapid inflation where all of the matter in the universe was together to explain the uniformity that we see today. Here to help us understand that, Alan Guth.
Thank you. Okay. To describe how inflation fits into the Big Bang picture,
I will escort you to
I think the key word
if that's what you truly wish.
The word prequel. Inflation is a prequel to the conventional Big Bang picture. There's inflation way on the left, top left, cosmic inflation, at about 10 to the minus 30 seconds. It provides a story that precedes the expansion of the universe, the formation of galaxies, et cetera. And basically, where it fills in is an important point which Neil actually mentioned. The Big Bang Theory is a misnomer. What we call the Big Bang Theory scientifically really says nothing whatever about what banged, why it banged, or what happened before it banged. It really says nothing about the bang. The story, the classic Big Bang Theory is the story of the aftermath of the bang. It describes what happens after the matter was already uniformly expanding with the space along with it.
You use more technical terms. You don't say pre-bang, post-bang.
Not more technical. Yeah, you're right.
Slightly, okay. Yeah.
Please,
please continue, yes.
Okay, so the way in which inflation explains the bang is in terms of a very surprising feature of physics, and very surprising to most of us, which is the fact that gravity can actually sometimes act repulsively. Now, those of us who learned about gravity in high school and learned Newton's law of gravity probably think this sounds crazy, because Newton's law of gravity is purely an attractive law of gravity. But that got changed with the advent of Einstein's theory of gravity, which is the theory called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. And furthermore, modern particle physics very strongly indicates that at very high energies we expect there to exist the kind of states of matter that would produce the repulsion of gravity that general relativity allows. And inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity.
And can I just ask you, so the math of both the Big Bang and the way sort of Einstein presents how the universe works suggests that at high energy states, the gravity that we understand becomes an explosive force, pushing outward rather than inward.
That's right.
And so the question is, you go about trying to test how that would actually work in the time span of the immediate aftermath of the Big Bang.
That's right. That's right.
Please continue. I just want to make sure I was on the same page. This is always very terrifying for me. Okay.
Okay, good, good. I should add that the inflationary model depends heavily on another very peculiar property of physics, a property that I think most of us are not used to, which is the idea that energies can be either positive or negative. And in fact, the total energy of our universe is completely consistent with adding up to zero. Zero in a form where all of the positive energies are in the form of matter and radiation, all the stars and galaxies. As you probably know, mass is really just a form of energy, according to relativity, with the famous E equals mc squared equivalence. Any mass is equivalent to an energy, which is the mass times c squared. All of those are positive contributions to the energy. The negative contribution comes from the gravitational field that fills the universe. Gravitational fields actually have a negative contribution to the total energy. And as far as we can tell, the total energy of the universe is consistent with being exactly zero, with a cancellation of these positive and negative contributions. And that's very important, especially for this idea of a multiverse, because it means that you can produce universes for free. It costs nothing to produce a universe. The universe is, in some sense, the phrase I like to use is that it's the ultimate free lunch.
I actually really was impressed by the universe until you just said that.
That is right.
I'm sort of yawning as another universe.
What I really am saying is that the universe is a gigantic big nothing as far as quantities that we think are conserved, quantities that cannot be either made or destroyed. So universes can be made for free, as far as we can tell.
So the conditions that establish the Big Bang and produce one universe are equivalent to a Big Bang which produces infinite universes, based on the math that you explore.
Equivalent is maybe a little too strong a word. I'll bet Neil will object. But the same mechanisms, we believe, those of us who believe in inflation, that produce one universe can produce many. And as far as I'm concerned, that's the norm in science. I think there's nothing that we know that can only be produced once. So I think this just proves that cosmology can be like other sciences. Now let me finish by describing some of the things that
All right, so that's it for another session of waiting for somebody to call me on Skype. Let me see. Did I get anything on chat? Anything? No, not on chat either, huh? That sucks. Yeah, well. So I guess we're gonna call it a day. Well, not a day, but I'll probably come back tonight again and do another 2 hours on WoW. But until then, you know, we shall see each other. And well, no, I don't see you. You can see me, but that's about it, huh? Well, that's about it. All right, press the button, Frank.